The last section I'm going to talk about in this section is logistic models. So logistic models are used to describe situations where the growth or the decay of a dependent variable is limited. So for example, we call the C our carrying capacity because as P of t approaches C, that's when t gets larger and larger and approaches infinity. So our value can't get any larger than C. So A, B, C are constants. A is greater than 0, C is greater than 0. And the model is a growth model if B is greater than 0, or a decay model if B is less than 0. We call the absolute value of B our growth rate when B is greater than 0, and our decay rate for when B is less than 0. So let's take a look at what logistic growth and logistic decay look like. So if we have logistic growth, my value is getting bigger and bigger and approaches C, right? Y equals C, that's going to be my asymptote. I'm never going to cross that line. If I have logistic decay, we're going to be approaching 0. So let's talk about some properties of the logistic growth function. So first off, the domain is a set of all real numbers. And our range is the interval from 0 to C, because C is our carrying capacity. There are no x-intercepts, and our y-intercept is at when time is 0. We have two horizontal asymptotes. That's y equals 0 and y is C. If you want to go back and take a look, here are our horizontal asymptotes. Y is 0 and y is C for both logistic decay and growth. P of t is increasing function if b is greater than 0, so if we have growth, and a decreasing function if b is less than 0, so if we have decay. There's an inflection point at on the graph that's 1/2 of our carrying capacity. The inflection point is the point on our graph where the graph changes from being curved upward to curved downward for growth functions, and for decay functions it changes from being curved downward to curved upward. This graph is smooth and continuous, meaning I can draw it without picking up my pen, and it has no corners or gaps. So let's look at an example. Let's talk about fruit flies. So fruit flies are placed in a 1/2 pint milk bottle with a banana for food and yeast plants for food and to provide a stimulus to lay eggs. Thank you for being so detailed. Example problem in our textbook. Suppose the fruit fly population after t days is given by the equation P of t equals 230 over 1 plus 56.5 e to the negative 0.37 t. Let's state our carrying capacity and our growth rate. So our carrying capacity is 230. Our growth rate is the absolute value of our b, which is 0.37. That's our growth rate. I want to determine my initial population. So my initial population is when time is 0. So let's go to B. P of 0 equals 230 over 1 plus 56.5 e to the negative 0.37 t, but t is 0. That gives me 230 over 1 plus 56.5, which is 4. So I'd have 4 fruit flies to start. That's how it always begins, just a few fruit flies. Now, what if I want to know what my population would be after 5 days? That's when I plug in P of 5. And let's change to a less angry color. So P of 5 equals 230 over 1 plus 56.5 e to the negative 0.37 times 5. And that's going to give me, when I plug this all into my calculator very carefully to observe PEMDAS, right? That's going to give us about 23. So after 5 days, I have a population of 23. because you can't have half a fruit fly. You got to round it to a whole number because we're working with fruit flies. My next question is, well, that was 4. Okay. My next question is, how long does it take for the population to reach 180 fruit flies? So for that, I'm going to need to clear some space, because this is one where we're going to have to take the natural log of both sides. So I'm going to go ahead and clear this. So for part D, I know I want my population to be 180, and I wonder, when is my population 180? So I have 180 equals 230 over 1 plus 56.5 e to the negative 0.37t. Okay, this can seem a little daunting. I want you to solve this like you would any other rational function, right? The first thing you want to do is get rid of that denominator. It's not helping anybody. So we're going to multiply both sides by 1 plus 56.5 e to the negative 0.37t. And it takes a long time to write, but that's okay. So I have 180 equals 1 plus 56.5 e to the negative 0.37t equals 230. And again, remember, our goal is to get the e all by itself so we can take the natural log of both sides. First thing I'm going to do is so remember that this isn't 180 equals, this is 180 times. So I can divide both sides by 180. That gives me 1 plus 56.5 e to the negative 0.37t is 1.2778. I can subtract 1 from both sides. So I get 56.5 e minus 0.37t equals 0.2778. Now, I know I still need to get this e by itself. So I'm going to have to divide both sides by 56.5. We're going to move over here so we have some more room. That gives me e to the negative 0.37t equals 0.0049. I'm going to go ahead and take the natural log of both sides. That means I can move this exponent to the front. So I have negative 0.37t natural log of e equals the natural log of 0.0049. That natural log of e goes away, right? Because the natural log of e, I'm going to remind you this a million times, is 1. We can divide both sides by negative 0.37. And I get that t is about 14.4 days. So it would take about 14.4 days in order for our population to be 180. Note, things like population and days have to be a positive number. You can't have a negative population. It couldn't have taken you negative 4 days. So that's one way to definitely check your work, again, is just to make sure your units make sense. Yes, sometimes our examples are a little weird, involving fruit flies in a milk bottle with bananas. But we are really trying to model the real world, so we're not going to give you negative days or a negative population. That should be a clue that you made a tiny mathematical error. So again, I do have the examples written out. So as t goes to infinity, e to the negative 0.07t goes to 0. So p of t goes to 230. My growth rate is the absolute value of 0.37, which equals 37%. That was what we did for part A. For B, we determined our initial population by plugging in 0. That gave us 230 over 1 plus 56.5, which equaled 4. So there were initially 4 fruit flies. After 5 days, we would have a population of 23 fruit flies. And that was about 23 fruit flies. I did have to round that. For part D, how long did it take my population to reach 180? Well, I had 180 equals 230 over 1 plus 56.5 e to the negative 0.37. So I got 180 times 1 plus this. Just again going in and filling in the symbols for those of you to check your work who are not in my class and did not get the PowerPoint. Me pretending anybody else watches these videos. If you're not one of my students and you're watching this video, please say hello. I'd be happy to answer any questions you may have. And with that, this is the final video I'm making for college algebra for the rest of the semester. So good luck studying for finals exams, and I hope to talk to you all again soon.